Cool. There. I think we can get started now. Hopefully everything is recording properly. My picture up here seems to be flickering, but so be it. So welcome to day 19. We're almost at the end. It's what? We've got 3 weeks and we're all done. So this isn't recent. Dora is still not with me. I hope to see her tomorrow afternoon when I get home from work. This is down in Kingsburg from during break week. And in Dora's new snowsuit, she quite enjoyed it. Her paws didn't slip out of the thing. Anyway, what is today? Today is supposed to be Monday, although this is recorded on Sunday. And things happening. Well, it's supposed to be International Day of Happiness. Should be, why do we need one day of that? We should be happy every day. And it's Alien Abduction Day. All right. Does that mean this is the day they do all the abductions, or do we just celebrate being abducted? I don't know. Tuesday sounds like spring music for mental health jam. I have no idea what this is, but if you're on campus and you're trucking towards the student center at lunchtime, it might be worth stopping by to see what it's all about. I really have no idea. Let's get going here. So a few things on the go here. We have an assignment due on Friday. As usual, I do a tutorial on Tuesday, which I expect you don't participate in, but I know a very large number watch the video. And my recommendation, once again, you can use the tutorial as you do the assignment, but you try the question first. If you get the question finished and you want to check your work, you might look at that little clip in the tutorial, then turn it off, do the next question when you get stuck. Definitely go back to the tutorial and or other resources to see how to get things done. That week 10 discussion, we're in classification, but we're also next week doing evaluation. And this is start at the time of year we do course evaluations. You should have received an email from me inviting you to participate in a course feedback survey. It's for the most part written comments on your thoughts about the content of the course, about using Top Hat, about the way I've done assessments in the course. That's a little different. I don't have midterms and finals. That a variety of aspects of the way we've done the course. For the people that are particularly among other instructors, the other instructors teaching this course are all new. They need teaching feedback about how they're doing their work. I'd appreciate yours as well. And especially, how do I do engagement in an online course? I've seen suggestions on how to do that, but I haven't seen any that I can easily adapt to my class, or maybe I'm just not comfortable with. But it's really important. I do encourage you to give feedback. But as I was saying, these things, I do evaluation, I assign you letter grades at the end of term, but they're based upon a whole bunch of different activities I've had you do, and you've gotten numerical scores, and we convert the numbers to a letter. So we take a value estimation thing and change it into categorical assessments, an ordinal variable, that the different grades are different steps, levels to them. That I'm going to turn off my video because it's just too distracting. It keeps flickering. You don't need to see me anyway. You know what I look like. But so I'm putting you into categories saying you're excellent or very good or satisfactory or have you. Is the tools or set of tools that I'm using to do that actually appropriate? Does it do correct classification? Are those that end up being classified as excellent really excellent? Those that are being classified as failures, are they really failures? It's quite imprecise, I think, what we do. But like any classification tool, it's hard to do classification well. Next week, not this coming week, but the week after, I think they start the official university course evaluations, and you'll get a link in Brightspace to do that. And I'll keep after you to go and do it because almost nobody does. Very, very few students evaluate their professors. This is the only information we've got for performance evaluation of instructors. And if we're going to renew their contracts or do work with them in some fashion, it's essentially we have that. And you're the only ones who can do it. You can tell me stories about instructors, good ones, bad ones. I'm not allowed to repeat them or at least use them in performance reviews because it has to be documented and signed. That you're probably not going to put in writing what you say about an instructor and sign that letter. It has to be objective or authentic. Anyway, also talking about grades, check gradebook. Some of you are starting to discover you've missed things and are asking what can you do about it. So check into that. This is a slide that actually it's from material from a year ago. I haven't got an update for 2023, but I think this came from the Conference Board of Canada, asking employers across Canada what are the skills that they think are in most demand. Now, these would probably be larger employers, the corporate community. But if you go back a number of years, skilled trades was top of mind. And the other things, like leadership, management skills, and you'll notice analytics and statistics got into the list back then. And since then, it's moved up. It's now up at the top with artificial intelligence, cybersecurity. Those are really, really big issues today. To be honest, I think the biggest problem companies have, it's lack of leadership skills and proper management skills. They're really lacking. And they're so hard to teach. We can teach analytics and statistics and skilled trades. It's much harder to teach people how to be good and effective managers and leaders. Anyway, let's get going. We've been doing probability last week. Conditional probabilities are particularly important to us because they're chance of something happen given we know other things that have already happened. And that we looked at particular cases last time of this sequential nature, A given B, it means there's a sequence, that if all the events are sequenced and they all go in the same direction, you can build a tree to describe what goes on. And the trees are really useful for exploring all the different possibilities that can happen. That using formulas for dealing with probabilities, I think for most individuals, is more like solving difficult puzzles. And that's well, it can be fun, but do we have to always approach things as being complex puzzles when we can structure them and find simpler ways of doing them? And trees are a way of structuring and finding a simple way to do things and avoiding formulas. That most of us like to look at concrete things, and we think in terms of frequencies and individuals that fit into different groups. And the trees are a way of splitting that large group that we start with, 100,000 people getting a COVID test, and putting them into different categories. And we keep partitioning and looking at smaller subgroups as we expand out the tree. And just like a tree, it's really thick at the start, but the branches, they get smaller and smaller as you go out. But we're getting into smaller and smaller groups. Can we use that sort of idea of partitioning as a way of mining the data? And we'll look at that. Just a quick recap. So exploring things like a rapid test, we might start out imagining 100,000 people and say, well, what if, because we don't know how many have COVID. What if 1% had COVID, 99% didn't, and we get into the, oh, that's 1,000 have it, 99,000 don't. And the rapid test we looked at, we had an idea of how often it gave a positive test if you had COVID, how often it gave a negative test if you didn't have COVID. And we could look at all the different possibilities of tests happening. That we're actually using the multiplication rule, but this would just be simple logical reasoning. You should be able to explode this tree without understanding probability at all. And then summarize your results, make them into a frequency table. Again, we don't need to understand probability to be able to get a sense of, well, what's the chance you've got COVID given you get a positive rapid test? A lot of you, I expect, did a lot of rapid tests last winter, last spring, when we were all doing them like crazy. And we just presumed if you got a positive test, you had COVID. And if you got a negative test, you didn't have COVID. Well, guess what? If 1% of the population have COVID and you get a positive rapid test, there's only a 40% chance you've actually got COVID. 60% chance you don't. It's not as accurate a test as you might think it was. Better than nothing. That it gives us some idea of who might be at risk and who's not, but it's not. It's far from perfect. As I said, categorization, classification tools, like the way I've been trying to classify your performance in this course, are not perfect tools. We make mistakes. That going through this and doing that analysis, we can do it using a formula. Very complicated. The formula is known as Bayes' rule. And on Wednesday's class, we'll look at actually using this formula in a very simplified fashion to go and make predictions. Okay, but rapid tests are a classification model. Exams are a classification model. That sometimes they can work really well, and sometimes they don't. With the rapid test, it works really well if there are a lot of people with COVID, like last spring when 30% of Nova Scotians had COVID. Rapid tests were very, very effective. But in practice, you shouldn't always be using them, especially when there aren't that many people with COVID, because they give misleading answers both ways. That if you get a negative test, still doesn't mean you don't have COVID. If you get a positive test, probably also means you don't have COVID. It's really confusing. That we'll get into all those performance measures, that type of thing, next week. But this week, we're going to use what we did last week to give us ideas about other methods for doing classification. Okay. Before I get to that, a couple review questions from last week. So you've got a spam filter for your email that every system does, because we get lots and lots of spam out there. That actually even stuff is blocked before it even gets to the spam filter. So if you're using Outlook, that if you're using Gmail, if you're using the St. Mary's email system, that it'll block a lot of messages to begin with, that it's blocking out what it believes is definitely dangerous stuff. And then it goes through another filter where it's trying to separate ones that should go into your inbox and are valid messages from ones that should go into your junk folder because they're probably spam. And it uses a classification model. And that, let's suppose our classification model, like a rapid test, it's 98% of the time takes the spam and puts it into the junk folder. Good. And 96% of the time it takes the good messages and puts them into your inbox, which is good. But of course, some of the time it makes mistakes. So let's suppose there's a fair bit of spam. Maybe 40% of your incoming messages are spam, probably closer to 80 or 90%. If we were to build a tree and we're looking at what should be our first branches? What should those branches be? Should it be good message versus spam message? Should it be inbox versus junk? Should it be good versus inbox or spam versus junk? Where would you begin? So you're going to imagine 100,000 email messages coming in. And so at the very beginning, you want to be able to split them along those two branches. So if you started out saying inbox and junk, where to put it? Well, 98% of spam goes into junk. So that's not 98% of my 100,000 because not all of them are spam. I can't go and start counting right away with the junk folder versus inbox folder. But if I split initially on good versus spam, I know of the 100,000, 40% are spam. So 40,000 messages are spam, 60,000 are good. So I should be able to split it up in that fashion between the two. So I can do that first branching. Then I can take those spam messages and decide, well, what percentage go into my junk folder? What percentage go into my inbox? Because I'm told 98% will go into the junk folder, 2% then go into the inbox. So the first one, though, has to be something I can lay out without knowing anything about the other variables. So your first variable you use is the one that you can treat all by itself without knowing anything about the other variable. Does that help? I'm just curious. I'm talking with my hands and I don't know if that helps. Oh, I got a better picture now. Let's go and look at, here's the tree that I built. So it's the good spam. It's got inbox, junk, inbox, so on. And I've put the probabilities in here. The 2% that's at the bottom, it says inbox 2%. What is that if I was to write it out as a proper probability? Now, I know notation isn't emphasized in the way we're teaching the course, but this is important because this is a conditional probability that we're dealing with, or could well be. If it's a conditional probability, the way we write it's important. Is it the chance it's spam given it's in the inbox? Chance it's in the inbox given that spam? Chance it's spam and in the inbox? Chance it's in the inbox and spam? Which way? The way we write things is the 2%. It only applies if you came down the spam branch. I can't get to that 2% one if I'd gone down the good branch. So it's only if you went down the spam branch. So it's 2% is the chance you're in the inbox given you're in spam. The way we write that is with that vertical line in between. Okay, that to the right of that vertical line is the stuff that we know for sure. Is it stuff that's in the inbox or is it stuff that's spam? We know it is spam. And we want the second thing is on the left of that line. So it's like a formula with y is on the left, x is on the right. X is the variable you know how many units you're making. Y is the total cost of making them. So I know this one is spam. How much of the spam goes into the inbox? 2%. So the answer is B. I don't know if I made that clear or not. So let me go and do this again. Now, I've written it out here, but I haven't done it. I've left all these probabilities that I haven't done it. Like suppose I've got 1,000 messages, and then if I've got 1,000 messages, how many end up in the junk folder and how many end up in the inbox? You've got to end up somewhere. Is it 24%, 2.4%, 39.2%, or 41.6%? So imagine you've got 1,000 emails. How would you split it up? Okay. So I've got 600 that are good, 400 that are bad. Okay? I'm looking at what gets into the junk folder. So of the 600 good ones, 4% end up in the junk folder. Looks like I'm falling asleep, but it's just my picture is frozen. Try doing that again. Now my picture's frozen. So what's 4% of 600? It's 24. So 24 good messages are going to get to the junk folder. I've got 400 messages that are spam, and 98% of them get put in the junk folder. Yee. How do I work that out? Well, the easiest way is actually think of the 2% of 400. I can do that in my head. 2% of 400, that's going to be 8, 2 out of each 100. So 8 are going to get to the inbox, 392 are going to get into junk. So I've got 392 spam messages in my junk folder. I've got 24 good messages in my junk folder. I've got in total 416. The right answer is D. I don't know if that made sense. Oh, I'm back again. Okay. So what I'd like to look at is this conditional probability thing, this idea of a formula that chance we'd renew given things you know about the customer. And ideally, we'd like that probability to be very close to 1. So that if that probability for a certain group that has a certain set of characteristics, the probability they renew is equal to 1, means they all renewed. Makes my decision easy. I know they're going to renew for sure. Or if that probability was equal to 0, I know they don't renew. So I know that for sure. If that probability was 0.5, I don't know, 50-50. So it's hard when the probability is in the middle. Decisions are easy when those probabilities are close to 1, close to 0. So in classification, that's what we're hoping for, is pushing numbers close to 1 and 0. That when we did trees, when we were organizing things, we knew, were they good or bad? Did they have cancer or not have cancer? Did they have COVID? Didn't have COVID? And then we looked at what happens when we do tests, and we branched and we split things up. Right? That the and at the end, then we flipped it around the other way. So we started out knowing if they had COVID, and then looked at what test results we'd get. And our goal was to turn things around so that if we had the test results, could we predict that they had COVID? But the idea of branching still was useful in getting them into these groups that were reasonably homogeneous. Like if you looked at the tree we just had with the COVID, they ended up that if they ended up with a positive test, okay, most of them, or with the spam messages, should I say, if it ended up in the junk folder, that we had most of those junk messages were junk. It's good classification. And most of the ones in the inbox were good. That's what we'd like, is to find groups where most people in the group look the same. So what if we took, instead of focusing on do you have COVID or not, or cancer or not, or that type of thing, or you're spam or you're good, that I look at a variable and I just start out, take my data set, split it into 2 groups, and see if the groups I form are easier to work with than the ones that I had before. They're more predictable. That confusing, isn't that sort of what we've been doing? But it's different. Let's go through an example. So we're looking at a customer and trying to guess whether or not they're going to renew their car insurance. And I've got many variables that I know about the customer. One of them is gender. So maybe I'm going to split them males and females and see, are one of those groups more likely to renew? I had 100 customers to start with. 60 of them renewed, 40 of them didn't. So it's almost 50-50. So it's going to be hard to guess if a customer is going to renew. So let's split them into by gender. Turns out there are 50 males in my group and 50 females in my group. So I split them that way. Let's look at the males. Well, among the males, 20 renewed, 30 of them didn't. That's just as confusing as before. That didn't help me. Look at the females. I got 50 females, 40 of them renewed, 10 of them didn't. Okay, that looks a little better. That it's still confusing about what males are going to do. But with the females, it's much clearer. Females are much more likely to renew. So if I knew the customer was female, I would guess you're probably going to renew. If the customer was a male, I'd say it's almost a toss-up. I'm not really sure. So this sort of process, this tree that I've been building, we use some jargon to describe trees when we're using them to make decisions. We start out, and where we begin, it's the root of the tree, and they call it the root node. A node, because this is what we're building, is what we call a network. A network is a bunch of nodes, spots, that are connected, okay? Connected by branches. And so like a road network, telephone network, all kinds of different types of networks of interconnection among different things. A neural network. That we take a node and we split it by branching. And we can branch into two groups, we could branch into more. We're going to stick to just using two groups. And when we branch from a node, we create what we call decision nodes, because those spots that we go to, we're going to be making decisions from. And either we can make a decision right now, or we're going to decide to branch and branch further. When we finally decide we're not going to branch anymore, so it's like the leaf at the end of the branch, we call it a terminal node. I'd prefer calling it a leaf. That at the end of a series of branches, that's what you get. So the jargon's not critical, but if you're reading other material, you need to be familiar with this sort of jargon. So with the males, I'm still no further ahead. So let's try another variable. Let's look at age. That if they're over 50 or under 50, age is a numeric variable. It's not categorical, but I've made it into a categorical variable. I've split it into under and over 50. That I don't have to. I could have picked a different value. But let's say I take 50, and then I look at those over 50 and see how do they compare to those under 50. Oh, there, I've got my mouth again. And then I could split further. I could look at, did they have an accident last year and file a claim, or did they not? Or maybe I look at the type of car they've got, or do they have home insurance with us? Do they take life insurance with us? Is the car an old one or a new one? I've got all kinds of different things that I can go and use as variables. Okay? So let's go and look at males. Suppose I split on age. And I've got 30 of them that were under 50. And among those 30, 5 of them renewed and 25 didn't. So if I know it's a male under 50, probably not going to renew. What about a male over 50? Well, 15 of them renewed. 5 of them didn't in that group of 20. So those over 50 are more likely to renew. Okay. So at the beginning, I didn't know a customer if they would renew or not. But if I know they're a male under 50, I would guess not going to renew. Male over 50, my guess would be they're going to renew. Females, I think they're going to renew, but let's drill down further. Let's look at their marital status. If they're married, I've got 32 married females. 30 of the 32, 30 of them renewed, almost every single one. So it's even better then. But if I know it's a female and she's married, almost guaranteed they're going to renew their insurance. But if they're single, oh my God, I'm back to where I started. I don't know what single females are going to do. That it's fuzzy again. But still, here I've been able to form these smaller subgroups that are much more predictable than the one I started with. So maybe with the single females, may look at their age, maybe look at their accident record, something else. That with those males over 50, I don't have to be satisfied with knowing that 75% chance of them renewing. I could split them. And if I looked at their accident record, 5 of them had accidents last year. None of them renewed. 15 of them didn't have accidents. They all renewed. This is perfect. If you're a male over 50, you had an accident last year, you're probably going to say, I'm leaving the company. I'm going to take my insurance somewhere else. But if you had no accident, then those over 50 are going to say, yeah, I'm going to stay with you. So this is much, much clearer evidence. This type of tree that we're building is called a decision tree. It looks like a probability tree, but instead of it being to explore all possibilities, it's to form subgroups, and ideally subgroups that are pure, that they're all the same. Like males over 50 with no accidents, every single one of them renewed. So it's pure. Everybody in that group is the same. Okay. That I'm hoping I don't get ones like the females that are single, where I don't know what to do with them. That one is very dirty, we would say, because it's almost 50-50 renew and not renew. I don't know what they're going to do next. So our goal is to get these nodes, these groups that are pure. And it's great because if we do, then we can set up simple decision rules. If the customer is male over 50 with no accidents, then this customer is likely to renew. But if the customer is female, single, under 30 with no accidents, then something else. If, then I make a choice. And it's just simple rules is all I end up with. That there's no fancy theory here, no math really. It doesn't have a lot of data problems with outliers and missing observations. I can still probably work with that. Very robust in that respect. And I could easily teach a computer to go and do it. Just write up some code so it makes the decisions for me. I don't need humans anymore to make decisions with this tool. It's like a probability tree. We're sequentially partitioning the data, but this one, it's quite different in terms of what we're doing with each of these partitions. Okay, we're trying to make groups that are easier to predict what's happening in the group. But how do we decide what variable to pick? Why did I pick age or marital status or accident record or something else? How do I decide how to split? I've got lots and lots of variables to choose from. In regression, we added variables by looking at correlation coefficients. That gave us a guide as to which one should be the next one we should look at. But what about what we do here? Well, there are some common methods for trying to see what variable best discriminates, separates people out into groups. And there are 3 that are very popular. That 2 of them are very similar, called Gini and entropy. We'll look at Gini. Entropy is a little bit harder on the brain. But then there's a thing called chi-square. Chi-square is something you'll see in a statistics course. And it's a way of measuring whether or not 2 things are related to each other. That it's sort of closer to this idea of different conditional probabilities, like I sort of used in the notes for the course. Gini is used in a method, a commercial method called CART, classification and regression trees. And chi-square is used in a method called CHAID. And I can't remember what all the letters stand for there. CHAID, if you've ever heard of Watson, IBM has an artificial intelligence system called Watson that's quite popular. and CHAID is one of the methods that it uses to do classification. Entropy has its roots in the second law of thermodynamics. It's part of information theory, it's part of engineering. I don't really know that stuff, so I'm not going to get into it. Each one works actually quite well. There's none of them seems to stand out as being consistently the best method to use. As we'll see with classification, there are no best practices in the sense of the tools out there, that there are lots of different ones, and some work better than others on some problems, and some days they don't work as well. So what is Gini? Let's look at one. And what do we mean by it's a measure of purity, of how clean a group is or a cluster is. So first, trying to explain what I mean by purity or how clean it is. If you look at the root node, it was 60-40, almost 50-50. When things are 50-50, it's hard to guess, is it going to be heads or tails? It's equally likely. You don't know what's going to happen. When I look down at females being 40-10, it was 80% renewed, 20% didn't. So I could say, they're more likely to renew. It's in that sense, the decision is clearer. It's cleaner in that sense. It's more pure. And if I look down at females that were married, 30 out of 32 renewed their insurance. It's almost guaranteed they're going to renew their insurance. I know what decision to make there. You're going to renew. And sometimes I'm wrong, but not very, very often. It's very, very pure in that group. Okay. That it's not a really diverse group here. I'm trying to get, in this sense, purity, everybody being the same, if possible, in that box. So how do I measure that? I can picture it now. Let's come up with a measure. Well, Gini is measured with a formula that 1 minus p squared plus q squared. What does that mean? So let's say p is chance you say yes to something. Yes, you're going to renew your insurance. And q is the opposite. No, the probability you're not going to renew your insurance. If everybody said they were not going to renew, then p would be equal to 0. Look at it in your formula. 0 squared plus 1 squared is 1. Subtract from 1, I get 0. My Gini score is 0. Okay? We have pure no. That if everybody said yes, they were going to renew their insurance, then P would be equal to 1. Q would be equal to 0. And so I'll get 1 squared plus 0 squared, which is 1. Subtract from 1, I get 0. My Gini is 0. But if P was equal to 0.5, half the people renewed, half of them didn't. I don't know what this person's going to do. I'm going to end up with 0.5 squared plus 0.5 squared. That ends up adding up to 0.5. Subtract it from 1, I get 0.5. This relationship between P, the chance you're in that group, and Gini is one where it's pure at the start, and then as that proportion that are yeses gets closer and closer to 0.5, Gini gets very close to 0.5. But then as it passes 0.5 and starts getting larger and larger, the closer it gets to 1, once again, Gini drops down to 0. So Gini scores, if a group has a Gini score close to 0, it's very, very pure. If a group has a Gini score very close to 0.5, then it's very dirty. It's very impure. It's going to be hard to make predictions. So I recently put together a summary report of what you answered in the survey at the beginning of term about yourselves, and compared it to the previous 3 surveys, and sent that summary to the dean, to the vice president academic, to several directors of student services, various offices, to tell them about what you're like and how you compare to previous groups. One of the disturbing findings is and this is one that has not changed during the pandemic, is almost 30% of students report each year that their fall term experience was below expectations. If you got 30% of your customers saying that they're really not satisfied with the experience they had, it's not the experience they were expecting, then you've got a customer service problem. So if we were to take actions to improve service, we'd need to have an understanding of who is it that's unhappy? How do we identify them? Because they're not telling us this unless we survey them. So I started exploring your data using pivot tables and tried to find what variables seem to have different levels of satisfaction. And I found those of you that had a GPA less than B, less than 3, weren't happy, or were less happy than those that had a GPA higher than B. That those of you, when you were asked what's the most important reason that you chose St. Mary's, was it the cost, the location, the program, the reputation, your friends? Program was very, very popular. Half of you picked it. But it was interesting. Those that picked program were generally much happier with their experience than those that picked other reasons for coming here. So, and then depressed at least once a week. People that are having maybe mental health problems, they're probably less happy and they're probably more disappointed. Yeah, that's the case. That people that are unhappy with life are also unhappy with their program, it seems. And there are a bunch of other variables as well that I've picked out. So I'm starting to study them. Haven't built a good model yet, but I'm working at it. So I thought, let me try using Gini and do classification. So I didn't take all of the respondents. Many people didn't answer all the questions. So, and I needed answers to the questions to start working through this. I looked at 1,000 students that I had pretty much complete data on. Of them, about 28% had their experiences were below expectations, and 72% had we met expectations were above. So if I'm taking this first group of 1,000, how clean is it? If I was to randomly select a student, could I predict very well if they would be happy or not? So the Gini score, when I put this into my formula, is 0.4. That's pretty high. Means my predictions are not going to be that great. So let's suppose I decided, let's split on GPA. I'll look at those with a GPA below 3 and those with a GPA above 3. Of the 1,000, I had 366 below a B, 634 above a B. So about 2/3 had a GPA of 3 or above. What do those two groups look like? Well, of those below a B, 44% were unhappy. That's pretty high. So those below a B were much less happier than average. And among those above a B, 19% were unhappy. So on the other hand, 81% were satisfied. So students above a B are more satisfied. Those below a B are less satisfied. What does that look like in our tree, and what does it look like in our Gini? So 1,000, okay, 28% below expectations. I split them into 366 that were on GPA, and then 634 that were above a 3. Gini scores for the two groups. Those that were happy or got good grades, should I say, had a Gini score of 0.3. That's a big improvement. On the other hand, that those that had a GPA below a B, the Gini score was worse. It's almost 0.5. It's 0.4928. It's going to be even harder to make decisions on that group. Was this a good split? It's better in one group, it's worse in the other. So I should average them. But the two groups are not the same. I've got 2/3 of my students have GPAs above 3, a third are below. So I should take a weighted average to weight those two groups. And so I weighted them based upon the number of students. And my weighted average is a 0.375 is my Gini score. So it's better than no split at all. So it's something we should consider doing. But shouldn't I look at other variables too? Maybe I should be looking at depression. Maybe it discriminates better. Well, I had of those that of those 1,000 students, 210 were depressed weekly or more. That's high. 99% or 47 or 99 of them, 47% were unhappy with their experience. I had a Gini score of 0.498, super high. Half of them are unhappy. Of those that were not depressed, often, that 19% it was below expectations. Okay, so I'm doing better with that. Or sorry, it's 23% below expectations. So I'm doing better with that. And so my Gini score ends up being 0.35. Okay, again, on average, though, I'm 0.38. It's still an improvement, but GPA was a better thing to split on. So I'll split on GPA, and then I'll try looking at other things. So I did that. And then I started looking at those that can I split up the ones that I had trouble with. 366 with a GPA below a B. And let me try the depression, seeing if that helped differentiate. Yeah, a little bit. It's a little bit better. Not a huge improvement in terms of the Gini score. Again, a weighted average, it's down to 0.47. But you can see that if you've got a low GPA and you're depressed, 64% of those people are unhappy. But if you've got a low GPA but you're not depressed, it's 38% are unhappy. Still a lot unhappy with their program, but not as bad as before. So I could have looked at program as well. I didn't look at that before. And when I look at splitting on program, and looking at those students with low grades, again, I go through, it's not as good a discriminator as depression. So, and I can do the same thing with those above B. This is tedious, as you can see. I start getting different Gini scores as I go, okay? With those above a B, splitting on program helps me even better. I'm getting down to that 15% below expectations if program is important to you. If something else is important, then okay, it's 0.375. I'm not as good as I was before, but it's improving. And I'm gonna have to keep splitting more and more and more work, okay? So I'm looking at the average improvement in Gini, and split may result in one of the nodes being much better than before and the other one being much worse, as we've seen. So we need to do that average of those things and look at, do we get an overall improvement? That notice one of the ones we used was GPA, and it's a numeric variable. I split it 50. I could go and then say, well, of those, sorry, I made a split at B at a 3.0. I could have gone and looked at those with a GPA above 3.0 and split between those between 3 to 4 and 4 to 4.3 or some other cutoff. I can split further and further if I want to. I can be more granular and recycle that same variable, but with a more granular split. Our goal is trying to get nodes, though, where everybody says the same thing, or almost everybody does. That it gets challenging, okay? we may have difficulty in doing this really, really well. So far with your data, I've been able to do some basic causal analysis. I can find things that drive satisfaction or dissatisfaction, but so far I've not been able to combine those to make a good predictive model so far. We'll see. Maybe I'll get better at it. Again, when trying to decide how to do a split, look at your different variables that you've got available to you, look at their Gini scores, and be greedy. Pick the one that seems to make the most improvement for that split. Okay? It's sort of like with a regression when picking the highest correlation. It's not a perfect approach to take, but it seems to work quite well. Okay? And each time we're only doing a split, it's if it improves our model. Just like with regression, if our R-squared is not improving, then we shouldn't bother adding the variable. We do have challenges with this, though, that each time we split, our subgroups get smaller and smaller and smaller. That group of 1,000, I split it into other groups, it's down into groups of 100, 200, 300. If I split again, I'll have groups of 50 or 75. If I split again, I make it down to a group of 20. Those are pretty tiny groups. That many would advise you to stop splitting when your subgroups get too small, maybe less than 50. I wouldn't want to work with more than or less than 50. I don't like tiny samples. If you have millions of data points, you can do an awful lot of splitting, but you may end up with a super complicated tree because there's just so many branches you can get. You may want to put limits on how far you go. Do you want to have a maximum of 10 variables that you're splitting on, or 100 variables? So some people put limits on that. We have to be worried about overfitting. That means fitting the model perfectly to the data. You've split, so you're down to groups of 1 and 2. Well, that doesn't make sense. You're actually describing specific individuals you've drilled down so far. You can train your model so it's perfect on your training data set, but when you go and try to use it in practice, it doesn't work. We'll talk about that next week, but as to an example of overfitting and so on. But in practice, what we'll often do is instead of using all 1,000 data points, I'll use 800. I'll train my model on the 800 so it works really, really well. And then I'll test it on the 200 that I haven't looked at and see how does it work in practice. And it's a safer way to do things. So my trees are a sequential way to split joint events until I'm getting down to what we call pure clusters, as pure as we can get them. It's sort of like a discriminant function, like splitting them, building a fence. But it's a rule-based one. If this and this and this and this, then this happens. And there are different strategies for splitting, but they all have branches. They're all somewhat different, but they're all at the same time somewhat the same. With very large trees, you can end up with super complicated rules, and you're also susceptible to overfitting. Okay, you've gone too far. But still, these are quite easy to use. They're easy to explain. They're easy to implement, and very often they work very, very well in practice. So next class is going to be our last one we're going to do on modeling classification. And we're going to look at those conditional probabilities and try to look at it in the context of Bayes' rule. And Bayes' rule, when you've got a lot of variables, not just A and B, not just 2 variables, but if you had 10 variables or 100, it's really complicated. So we're going to try to come up with something that's simpler. And we're going to simplify the theory. We're going to make assumptions that aren't true. We know they're not true, but they make the math simpler. And then see, well, if we take this simple-minded approach, will it actually work? Simple-minded, that's in a sense what we mean by naive or being simple-minded. We're not recognizing the complexities of what we've got. But it turns out that being simple-minded doesn't mean you're going to get bad predictions. There's some interesting results that come out. So that's where we are. We're going to end it there and leave it for the next class.